Okay, let's start. Are there any questions from last time before we continue? Okay, so let me remind you, we were discussing free Maxwell theory in D equals 4 Euclidean dimensions, 3 plus 1 dimensions, which in the electric presentation, the standard one looks something like this, where F is the field strength. And one of the things we said is that this theory has two one-form symmetries whose corresponding two-form currents are up to factors F and star F. The reason I'm putting the stars in this Baroque place is because you integrate star of the current over a 2-cycle in order to get the corresponding charges. So this integrated over 2-cycle is the electric charge, and this integrated over 2-cycle is the magnetic charge. All right. So this theory has two one-form symmetries. And then we had a discussion about the operators in the theory that are charged in these symmetries, and we said that they are line defects, line operators. And in particular, they're line defects that have the property that when you link them with a small 2-sphere, that when you integrate these fluxes over that 2-sphere, you measure the electric and the magnetic charge of the line defect. Very good. So the thing that I want to discuss next is the question of whether or not these symmetries are spontaneously broken or whether they are unbroken. Remember, that was a basic and important question about ordinary symmetries, and it's also the question at the heart of the Landau perspective on phase transitions. And so it's a natural question to ask. I will start this discussion a little bit backward. We'll get back to this very direct question in a second. I'll get back to the question in a slightly roundabout way by asking a question that is sort of like standard and familiar in the way that people usually discuss phases of gauge theory. So sort of, before things were reformulated in terms of higher symmetries, the sort of paradigm of how to understand phases of gauge theories, which was laid down by people like Wilson and others, was that you should try to understand, the behavior of Wilson and 't Hooft loops, but first and foremost the potential between heavy charged objects. You should consider putting heavy charged electric things and heavy charged magnetic things and ask what is the force or the potential between them. And this is a fundamental quantity which you can calculate on the lattice and all over the place. It's a kind of central ingredient into the subject, so I wanted to show it to you. So in principle, we can consider the potential between anything we like, but the most standard setup is to consider the potential between some source Q and its conjugate, its CPT conjugate. So if you have something that has electric charge, then Q bar would have negative that electric charge. So imagine that you have something like this, and you can ask, if you separate these objects by a distance r, what is the potential between them? And as we'll see, this is not far removed from the question I was asking before about whether or not the symmetry is spontaneously broken, so we'll see that there's a relation. Now, in this setup, Q could be a dynamical charge. For example, if you have an actual dynamical electron, like in QED, you could try to compute the potential between two electrons. But even in Maxwell theory, right, we've learned that there are probe charges. There are Wilson lines, for example, or 't Hooft lines, which represent static, non-dynamical charges. And there's still a valid question to ask, which is what is the interaction energy between them that's mediated by the Maxwell field. Okay? And so that's what this quantity probes. Very good. Now, in Maxwell's theory, this is pretty easy to compute. So let's, for example, take the case when Q is an electric charge. Then this is nothing but the Coulomb potential. Right? QE bar is minus QE. So this is just up, well, to some factors of 4 pi, which I'll definitely not get right, and which are also not important for what I'm saying. This is just the attractive Coulomb potential between a charge and its conjugate. And it's easy to do the calculation for a magnetic charge as well. You can just take this formula and you can apply duality to it. The E will go into the denominator because of the duality, and then you'll get a Qm in the numerator. So you see that up to the different factors of E and so forth, these are very similar formulas. And this fact that the potential between charges has Coulomb law is what leads to the sort of standard terminology that this theory is in a Coulomb phase. And any theory that we find that has this Coulombic behavior at long distances is said to be in a Coulomb phase. So roughly speaking, a Coulomb phase is anything that has a Coulomb law. We'll get a slightly more precise definition of what a Coulomb phase is once we relate it to the higher symmetries. All right, so now we can get back to the question, as of yet not obviously related, question of whether the higher symmetries in Maxwell theories are broken and unbroken. And if you've been staring at these formulas, you might have been tempted to come up with an obvious answer. The obvious answer is that these formulas for the charges are linear in the fields, right? F and star F. So in particular, when you act with these currents in the vacuum, you create a single particle state. This is a free theory. And F is the field. It's linear in the creation operator. So you create one photon. And it's the same for both of them. You create different polarizations of the photon, two polarizations of the photon, which is what is responsible for having the two currents here. And you can create both of them by acting with the currents. So remember that I reviewed for you very briefly what happens in the O2 model, and this is completely generic for spontaneous symmetry breaking of ordinary symmetries, which is that at low energies, the currents are dominantly linear in the Goldstone boson fields, right? The currents acting on the vacuum give you a single particle Goldstone boson pole. This is the bread and butter of current algebra of Goldstone boson physics in almost any context. And the same is true here. So this fact alone is essentially an argument that these two symmetries are both spontaneously broken. So that's argument number one. Argument number two is a little more involved, and you can ask, well, instead of using the fact that I know that the currents are linear in the Goldstones, which is a little bit of an indirect argument, you might ask, well, just show me directly what is the expectation value that breaks the symmetry, right? If there's a symmetry that's spontaneously broken, we should have some kind of charged operator that gets an expectation value. And in the case of the O2 model, for example, we could say, okay, you have a charged field phi, right? It has U1 charge, and then this field can get an expectation value, and then the U1 symmetry is spontaneously broken. How do you detect this expectation value? Well, one way to do it is to literally study the one-point function. You could just try to compute the one-point function and see whether it's 0 or not. A trick that's often very useful, even when you're studying ordinary symmetries, is to not study the one-point function, but to study the two-point function of phi and phi dagger. This two-point function, of course, is not charged. Otherwise, it would be 0, right? Phi and phi dagger have opposite charges. So as a whole, this two-point function isn't charged. But you can still infer the vev of phi by clustering this two-point function. So if you, say in Euclidean signature, take x to infinity, then at leading order, this will just give you the vev of phi squared, and then you'll get connected contributions which decay with x. How fast they decay depends on your theory. Maybe they decay like power laws in a gapless theory, or maybe they decay exponentially if the theory is gap, but the leading long distance contribution is the VEV squared. So by looking at this 2-point function and clustering it, you can determine whether or not the symmetry is spontaneously broken. This is a kind of standard argument. For example, this is also the convenient and quick way to prove the Coleman-Merman-Wagner theorem in 2 dimensions, the fact that there is no spontaneous symmetry breaking. You look at the correlation function of these operators and you see that you never get this unit piece. All right. So in the context of one-form symmetries, the standard argument or the standard rule that people formulate in order to detect whether or not a loop operator has a VEV, the analog of this statement, but now for a loop. Right now we want to generalize this to a situation where we have a one-form symmetry and the operator whose VEV we are studying is some kind of loop. Could be a Wilson loop, could be a 't Hooft loop, but it should be charged under the one-form symmetry. And the rule that people typically formulate, which is related to the behavior of large closed loops, and I'll tell you about it in a second, is really the analog of this. It's not the analog of this. Okay? The reason that's the analog of this is that if you take a large closed loop in the plane, where you can put it anywhere you want, but take a large closed loop like this. If there's no interesting topology anywhere in the spacetime manifold, let's say we're in R4, then this loop is not actually charged under the one-form symmetry.
Why not? Why does it have to be large anyway? What does it mean large? We are in infinite space. Large compared to what?
Whatever mass scale of your theory.
There's no mass scale. It's we are in Maxwell theory for dimensions.
Okay, so there might be some scale invariance. Maybe in this theory things will be scale invariant, but in a generic theory that would not be the case. If I'm in infinite volume, I'm certainly in order to extract the VEV from the 2-point function, I need to take some limit like this.
Because the loop has both part that go that way, and
right. The loop is closed. So as long as the loop doesn't wrap a closed cycle, if you're for example on a torus and the loop wraps a closed cycle, then it is actually charged under the one-form symmetry. But if you have a contractible loop in 4 dimensions, let's say, then this thing doesn't actually carry any net one-form charge.
I'm confused because you last time you can surround the loop by some sphere, you shrink it, and it's going to get you the charge of the object which propagates around the loop. So you explained to us last time how to compute the charge of a loop.
I'm using the notion of charge in slightly different ways. So let me be more precise to tell you what the difference is. The definition I gave then was a kind of local definition, right? What I'm trying to argue for you is that a closed loop like this is the analog of this. All right? This 2-point function has 2 pieces. This piece is charged, and this piece is charged. So locally, this bit has charge +1, this piece has charge -1. And similarly, like each local bit of loop carries electric charge. But if you try to implement a conserved charge that measures the sort of total one-form charge in a flat R3 slice, that is the Gaussian flux integral at infinity. And from the point of view of the Gaussian flux integral at infinity, this loop doesn't carry any charge. Because roughly speaking, it has bits that carry charge 1 and bits that carry charge -1. And it's the same with this. From the point of view of an observer that measures this correlation function out here, this doesn't carry any net charge. There's another way of arguing for what I just said. Imagine you take a Wilson loop, which is the simplest example, right? Then if the loop is contractible, you can simply write it as e to the iq times the integral of f over some bounding surface.
But I totally understand that if you take, of course, a big surface at infinity, that has the charge, but is it clear that that's the correct thing to do? Why can't you take a small surface which surrounds just a bit of a loop which locks
These are different things. So I am now asking about spontaneous breaking of the charges that actually act on the Hilbert space. And that act on the Hilbert space in flat R3 quantization. And the charges that act on the Hilbert space in flat R3 quantization are the Gaussian flux inequivalents at infinity.
Yeah, can I ask a question along the same lines? Why can't I wrap it with a tube?
No, you can do more sophisticated things, but if you're a person who wants to know the phase of the theory in flat space, this is the kind of question you ask.
But wouldn't this also measure the one-form charge of the symmetry?
No. The thing that you should be a little bit careful about is that, so I've been taking a predominantly Euclidean point of view, and when you do that, you can wrap the charge on anything you want. But when you're asking a question about spontaneous symmetry breaking, you are really talking about the Lorentzian signature, there's a Hilbert space, and there's a charge, and you'd like to know, is that charge acting on the Hilbert space broken or unbroken, right? So I would like to know, this is the analog of really, taking the integral of J0 in an ordinary symmetry case and asking whether it's broken or unbroken on the Hilbert space.
Yeah. What if you consider a not closed loop, but just a string that goes to infinity on both
Very
sides,
good.
then it will be charged?
Very good. That's the thing that will be charged. So if you want something that's genuinely charged, right, as I said, the Gaussian flux integral at infinity is the charge we're talking about, then the analog of this is actually a loop that goes, so imagine that spatial infinity is a kind of two-sphere that I'm drawing here. So this is spatial infinity. Then a loop that does this, and goes from one point at spatial infinity to another point at spatial infinity, that one is actually charged on the one constant.
Then if you simplify what you just told about this being not charged, if I start to slice it from top to bottom on R3 slices, in each R3 slice I will have 2 points and their charge will cancel each other.
That's right. So one way of thinking about this is that as you make this loop very big, let me tell you where I'm going, because where I'm going is the standard rule, the standard prescription that if you take this loop to be very large, then its asymptotic behavior is going to tell us whether or not this thing has a VEF. Now, the way you should think about this is that when this loop becomes very large, it sort of clusters into like products of these kind of things. Now, of course, the idea is that the answer you get doesn't depend exactly on how you do the clustering. You might have to pick a specific shape. You might have to take the limit in a particular way. Usually people take kind of nice things like circular loops. But roughly speaking, when this large loop hits kind of infinity, it's going to try to cluster into things like this. And whether or not you get a non-zero answer will tell you whether the charged things themselves are zero or not. Right. The reason that I'm emphasizing that in a little bit of detail is precisely because it's generating the confusion that we're having, because in the standard recipe for determining whether or not a one-form symmetry is broken or unbroken, the object that people discuss is always uncharged under the symmetry. So it's a little bit funny, and one has to do this. One has to say these extra words in order to get from one to the other. Okay. Any more questions? Yeah.
So is that thing like wrapped in the torus?
No, this is still in flat space. So if you have a torus, then you can wrap cycles and so forth. Even in compact volume, you can have charged operators. But if you're in flat space, this is supposed to represent the spatial boundary of R3. This is the sphere at spatial infinity. So the reason you're allowed to have open Wilson lines, right, that go to spatial infinity is because the gauge symmetry is not actually gauged there. Right? This is a sort of standard thing in gauge theory. We mod out by gauge transformations that go to the identity at infinity. The gauge symmetry that acts non-trivially at infinity is actually a global symmetry. And that's why Wilson lines that go all the way to infinity are actually gauge invariant. Right? Normally, open Wilson lines are not gauge invariant. Right? They transform non-trivially on both ends in conjugate representations. But if you take them all the way to infinity, it's okay. And then these infinite Wilson lines are actually operators acting on the Hilbert space.
Sorry, maybe I have a different question. So those points at infinity should not be thought of as identified from each other?
No. They're different. One is over there and one is over there at infinite distance.
Say if your system has a homosymmetry, this infinity point can be moved to finite space. Is the infinity here well defined in
I think you have to be careful when you do that. For some purposes, it's okay to do that, but for some purposes, you have to be careful. I'm studying the theory in the most naive way, just being a person who lives in flat space and asks questions in flat space. Using conformal symmetry, you can, for example, potentially map these kind of correlation functions to correlation functions in a closed space. And then there's a question of how you take this limit. The tricky part is how you take this limit. Very good. Right. So backtracking a little bit, the thing that I would like to say is that you should study the limit of this kind of observable, right, the expectation value of the closed loop, when the loop becomes large. How exactly the loop becomes large is hopefully not going to matter. Right? In principle it matters, but just like it ultimately doesn't matter how you take x to infinity in this kind of problem. So typically people take some things like square loops and circular loops and so forth, but in principle you should be able to take any loop you want. And then you scale it up in some way, and you ask whether or not in that limit this loop expectation value has a non-zero VEV or it just decays to zero. That's the basic prescription. Now, the second caveat that we have to discuss when we talk about loops is that VEVs for loops are not quite as straightforward as VEVs for local operators. If you have a local operator like phi, and you tell me that it has a VEV, then that's good, and then I know that the symmetry is spontaneously broken. And I cannot modify that statement by kind of changing my renormalization scheme. So imagine that you and I have different renormalization schemes, then our definition of the phi operator might differ by some wave function renormalization. So there's some kind of factor that I can multiply phi with in the definition of the operator. But this multiplicative constant doesn't change whether or not phi has a non-zero expectation value. If one choice of phi has a VEV, then the other choice of phi will also have a VEV. Now, in the way that I've just defined the VEV of the loop, where you simply look at the expectation value of this L as the loop becomes large, and you ask whether it's zero or not, that actually is a little bit ambiguous. That's a little bit scheme dependent because the counter terms that can modify the expectation value of the loop are not just constants, they can depend on the shape of the loop. Okay, so let me say a word or two about counter terms. I'll do it here. Well, without going into too much meta discussion about defects and locality and so forth, it's kind of reasonably intuitive that the allowed counter terms that live on the loop should be some kind of like local geometric invariance of the loop. One way to understand that is to imagine that the loop comes from integrating out a very heavy particle. Then the heavy particle would kind of couple to the ambient geometry, if there is any, and to the extrinsic geometry of the loop. And it could generate counter terms on the loop that depend on the geometry of the loop. For example, the most standard counter term, which is the one that will be most important for what I'm going to say, is just the length of the loop. So we have loop counter terms. And you can simply modify the loop by multiplying it by e to the minus m times what's usually called the perimeter of the loop. The perimeter of the loop is just the length of the loop. Right? With respect to the induced metric on the loop. So if we're in flat space, it's just the standard length. This parameter m has dimension of mass, right? P is a length. this M has as dimension of mass. It might be finite, it might be infinite, depending on your scheme. It might be positive or negative. M doesn't have a preferred sign either. Roughly speaking, M is like a mass renormalization for the infinitely heavy particle that you integrated out to make the loop, schematically. There are also higher derivative counterterms that you could contemplate for the loop that involve not just the length of the loop, but things like the extrinsic curvature. But these higher derivative counterterms are also pressed in the cutoff. So if you think of M as being a kind of UV cutoff type scale, then all the higher derivative counterterms would be 1 over M suppressed, 1 over M squared suppressed. So you don't need to discuss them in the continuum. You could ask whether there are any marginal counterterms, and the answer is that generically there aren't any except in 2 dimensions where one has to make a separate argument. Okay, so by modifying the loop in this way, right, we can affect its long distance behavior, because as we scale up the size of the loop, right, this thing goes to infinity. So that means that if M is positive, this thing will be exponentially decaying with the length of the loop. If the M is negative, then this will be exponentially increasing with the length of the loop. So we need to modify somewhat what we mean by the loop having constant VEV. What we mean is that in the universality class of loops, where you allow yourself to add such perimeter counterterms, right, there's one representative that has non-zero VEV, and then all the other ones could decay or increase according to this perimeter law. So the general rule that people formulate is what's called perimeter law. If the loop behaves, the large loop behaves like e to the minus mp for some m, then it's equivalent to saying that there's a scheme in which the loop has a non-zero VEV, right? So we say that the loop has, we say that this has a non-zero VEV. Come on. Really not the loop. We say that the clustered operator has a non-zero VEV, and in this case, in particular, we say that the one-form symmetry acting on the loop is spontaneously broken.
So does it mean there are multiple vacua, like in zero form symmetry, and then the degeneracy of the vacuum can rotate phase of the condensate?
That depends very sensitively on what your definition of a vacuum is.
There you can turn on a small perturbation in the Hamiltonian.
Exactly. So you cannot do that for these symmetries, and I'll explain that in just maybe 10 minutes or so. Because in this setting, there's no perturbation of the Hamiltonian that breaks the symmetry explicitly. So these are not standard kind of infinite volume vacua. We would still say that the infinite volume theory really only has one vacuum, but it has some kind of degeneracy coming from the spontaneous breaking of the symmetry, and that's been discussed from various points of view. For example, if you put the theory on a non-trivial spatial topology, like Max was doing yesterday for topological phases, but you could imagine doing it for this as well, then you get degeneracy associated with these loops. Or if you hear people talk about things like asymptotic symmetries and soft theorems and so forth, they're also related to the degeneracy associated with the spontaneous breaking. Yeah. But there's no... So one way of saying it is that if you study the Hilbert space on a very large sphere, there's a unique vacuum. If you study the Hilbert space on manifolds of higher topology, just like in the topologically ordered case, you would get interesting additional sectors coming from these loops.
Why is this easier than just taking the infinite line? I mean,
Well, roughly speaking, it's related to what Son just said. You know, because anything infinite is a nightmare. And anything infinite in practice needs to be regulated and carefully taken the limit of. And when you discuss standard spontaneous symmetry breaking, there are many ways of doing that. For example, one way of doing it is to do what Son said and add an explicit breaking in the Hamiltonian, a small deformation that breaks the symmetry. Then you land in some particular sector and you can compute, and then you take the limit. Another way of doing it is you can put a system in finite volume, put a boundary, and then you put a boundary condition that breaks the symmetry, and that also selects a vacuum. Well, let me put it this way. Somebody in the universe, if the symmetry is spontaneously broken, has to actually tell you which direction it's broken in. Right? Imagine you have a magnet or an O2 model or something. The VEV could be here, the VEV could be here. Who decides? Somebody needs to break the symmetry somewhere in the calculation. If you do the calculation in a way that's completely symmetric, you will never ever get a VEV. And so this is the way that spontaneous symmetry breaking always comes about. You put some small symmetry breaking perturbation, and then you take the limit to infinity, and then the perturbation. One way of saying what spontaneous symmetry breaking is that it's a symmetry breaking perturbation that doesn't go away even once you take it to zero. This scheme doesn't work nearly as well for these higher form symmetries. So I don't think this would be computationally straightforward, even in this free Maxwell theory.
May I ask a question?
Yeah.
So any other behavior is unbroken regardless of whether it's faster or slower than perimeter?
No, no. Only one direction is true, right? So if it decays faster than perimeter, then it's unbroken. But if it, of course, blows up faster than exponential in perimeter, then it's...
It doesn't have to be area, it can be something else.
It could be something else, yeah. So usually this dichotomy is framed in terms of area versus perimeter, but to my knowledge, there's absolutely no proof that these are the only two options. And in fact, I think there are even simple gapless theories that you can write down where the answer is neither.
If it's like the square root of the perimeter, that's slower but still grows. So I don't know if that's broken or unbroken.
Well, I would say that anything that you cannot make a constant with a perimeter counter term, well, you have to decide what it is. Either it goes to zero or it goes to infinity, right? It can't go to a constant. The only thing that can go to a constant is exactly perimeter. If it goes to infinity, I think it's definitely broken, very much so, right? Just grows. That's a little bit sick. I mean, we typically don't have correlations that grow at infinity at such a large rate, but I'm not sure.
Sorry.
Yeah.
And why can we add area counter term or something like that? Like m squared times area.
Well, the loop. So the area of the loop is not a local property of the loop. I want local counterterms, right? Local counterterms should be localized on the loop itself. They're like UV effects that are only sensitive to the geometry of the loop itself. The area is what is the area of the loop? There are many areas that have the loop as a boundary.
Perimeter is also changing depending on the loop.
I know, but it's local. If I tell you where the loop is, you can calculate the perimeter. The area is some kind of... The area hasn't even appeared yet. I think he's the only one who said area. I haven't even said anything about the area. I'm just saying that there's no the well-defined area. There are many areas that have the loop as a boundary, and any one of them would be like some non-local property. You'd have to go away from the loop to know what the area is.
So perimeter locally in the sense that it's only knows only about the loop itself.
Yeah. And it's because it's a UV effect, right? It's a regularization effect.
The area appears in the second blackboard, A.
Should never say things that you don't commit to.
I stand corrected.
Okay. So let's relate this criterion to the previous one that we had, the one that that involved the effective potential, right? We had the effective potential between a charge Q and its conjugate. We said that in Maxwell theory this decays coulombically. How can we relate this to this discussion? Well, there's a famous little thought experiment that due to Wilson that you can do that relates the asymptotic behavior of large loops to the asymptotic behavior of this potential. And in order to do that, the kind of loop you consider is roughly speaking, rectangular loop. You don't have to make it exactly rectangular if you don't like corners. You can smooth it out a little. That's not so important. But you take a large Euclidean Wilson loop that is extended in the Euclidean time direction, t, and then the other leg is the spatial distance r between the charges. And then if you take a loop of charge q that goes around like this, right? And you interpret it in Hamiltonian quantization with this being time. I should really have time going one way. Then you see that this loop going forward in time represents the charge q sitting here, and this loop going backward in time represents the CPT conjugate going down here. And roughly speaking, this piece of the loop acts as a kind of QQ bar creation operator that creates this particle-antiparticle pair with its concomitant flux at the initial time. If you smooth it out a little bit, this can be actually kind of viewed as a pair creation process. Here it sort of happens at one instance in time. And when you take t to be very large, you can argue, right? You can just argue using standard kind of Euclidean time evolution that this gives you a time propagation factor in Euclidean time that goes like e to the minus t times the energy of the configuration created here, and the energy of the configuration created here is this QQ bar pair. So you get VQQ bar.
Plus twice the mass of the quark.
Right, very good. So I haven't committed yet about counter terms and the mass of the particle and so forth. I'm assuming here we're still sort of in free Maxwell theory. There is really no particle mass, but there is this perimeter counter term. So let me include it, right? So I've argued here that any loop can be modified by a perimeter counter term. What does the perimeter counter term do here? Well, the perimeter counter term, if you take t to be, this happens in a limit where t is much bigger than r. So large Euclidean time evolution. So you project onto the ground state of this QQ bar system. The perimeter is 2 times t plus 2 times r, roughly speaking. And if t is much bigger than r, it's just a constant times t. And this constant just appears as a kind of V0 shift in the definition of the potential. So we see that we get something entirely sensible. The UV-dependent counter term that makes the perimeter behavior of the loop ambiguous is precisely the ambiguity in choosing a zero of the potential. Right. And I'm not going to commit what this constant is. I don't need to. Very good. Now, because we already set up there that up to constants, the potentials between electric and magnetic charges are coulombic in Maxwell theory, right? This thing decays at long distances, and you're just left with the perimeter behavior. So every single loop in Maxwell theory has perimeter law, and that's another way of deducing that the one-form symmetry is broken, which we already deduced from the Goldstone boson argument. It also tells you that the one-form symmetry is completely broken. There's no unbroken subgroup, discrete or otherwise. Yeah.
So B0 is the counter term that you said is the perimeter.
Mm-hmm.
Okay.
Up to a factor of 2 and so on. Yeah.
So we don't know from this the functional form, like 1 over r.
No. So depending on, this is a very general thing you can do in every theory, but the functional form of V is entirely theory dependent, right? You need to compute it. So in free Maxwell theory, it's easy to compute, but in other theories, it may not be easy to compute.
So Coulomb phase is not the same as spontaneous?
It is. It is. Coulomb phase, so we now have sort of three different perspectives on what a Coulomb phase is. The gut feeling perspective is that a Coulomb phase is something that has a photon where you have a Coulomb potential. The one way of saying what that means is that you have this electric and magnetic one-form symmetries, and on top of that they're spontaneously broken. So that the photon is actually the Goldstone boson for these spontaneously broken symmetries. And the third perspective is this one.
So they just said this is not equivalent to like the potential having.
No, but as long as the potential goes to zero sufficiently quickly, then those symmetries will be spontaneously broken. And in the moment you know that the symmetries are spontaneously broken because they're U1 symmetries, you can prove that you actually need a photon. The reason is that you know the moment you know that the continuous U1 symmetries are broken, you act with the U1 current on the vacuum. You do the sort of standard spectral decomposition argument that people use to prove the existence of Goldstone bosons, and then you can infer the existence of a photon. And once you know that, you can of course go back and say something about the potential. But not every theory that has a photon at long distance is free Maxwell theory. There are some theories that have charged matter and so forth, and they also have a photon at long distances. For example, QED. And in QED, the potential is not exactly Coulombic, right? It gets radiative corrections and so forth, but it still decays to zero at infinity.
So the potential is linear, so it's not broken.
If the potential grows faster than perimeter, linear is an example, but there are many functions that. So from the point of view of the potential, anything that beats this constant, anything that grows at infinity, is unbroken symmetry.
Oh, so can we only broke one of the U1 one-form symmetry? Is there a possible here?
You mean to break one and not the other?
Yeah.
Well, in this theory, we can't do anything because it's free. So we're going to have to modify the theory in a variety of ways. And when we modify the theory, we typically, before we ask about spontaneous breaking, we'll first break some of the symmetry explicitly. Okay, that's the thing we'll have to figure out first, and we'll do that soon. Then once you know for example, you can add matter, right? You can add matter fields, but in that case, the full U1 times U1 symmetry will not survive. So first you have to figure out what is explicitly broken, then you can ask what is spontaneously broken. All right.
Stupid question, but the expression that you've written there on the right-hand side on the left blackboard, isn't that's not gauge invariant, right? Because it has the potential in it.
That I think was the only mistake in that for you. Sorry, I don't understand the question about gauge invariance. Everything is gauge invariant.
You can do a gauge transformation, and then the whole expression on the right-hand side will change, right? But the left-hand side.
Why? I think the onus is on you to explain why. This, by definition, is the expectation value of this gauge invariant operator.
Yes,
so by definition, this number, this quantity here is gauge invariant.
Maybe let's let him continue. Because it's good to have too many questions, but we also want him to tell us what he wants to tell us.
Yes.
Sorry.
I can ask later, it's fine.
No worries, yeah. But just to be clear, I mean, there's no independent definition of this quantity. This is the definition of what I mean by VQQ bar, the end. Yeah. Okay, very good. Maybe I'll skip some of this stuff because I'm not doing so well in time today. All right. Very good. Okay, so the most important conclusion, right, we've said a few times, is that Maxwell theory is a theory where both the U1 magnetic and the U1 electric are spontaneously broken, and the photon is, in some sense, a Goldstone boson for both of them. That's related to the fact that the photon has two polarization states, and so you have two symmetries, and you get two independent propagating degrees of freedom that represent the Goldstone boson. Very good. So let's make a little detour and discuss something that we haven't yet talked about, which is anomalies. So we have two new kinds of symmetries, one-form symmetries, right? And we should ask, we should try to do everything with these symmetries that we do with ordinary symmetries. And as I said in the very beginning, one of the things you do with ordinary symmetries is you couple them to background fields, and then you can do all sorts of things. Once you do that, one of the things you can try to do is understand if there are 't Hooft anomalies between these global symmetries. And indeed, we'll see that already in free Maxwell theory, there's a kind of rich realization of that. So in order to do that, we're first going to have to understand how to generalize the notion of a background field from ordinary symmetries to higher form symmetries. And the generalization is fairly intuitive. I mean, we've said that the generalization involves going from an ordinary current to a fully antisymmetric current. So it doesn't come as a shock that the generalization of a background field goes from an ordinary, one-form vector field to something that has many fully antisymmetric indices, right? So this is a kind of generalized antisymmetric B field. And in the case that we're discussing, when we're discussing a one-form symmetry with a two-form current, the case that we're interested in are two-form background gauge fields. So we'll have background two-form gauge fields for the electric symmetry, and then we'll have a separate one with a magnetic symmetry. We have two symmetries, right, like momentum and winding in the compact boson. So we need two background fields for them. And these background fields, for example, they behave very much like the two-form background fields in string theory, except that they're backgrounds, not dynamical. For example, they have their own higher form version of gauge invariance. Under a background gauge transformation, these transform by D of a one form, except that these lambdas, these capital lambdas, are not really one forms. They're themselves U1 connections. So, for example, they can themselves have quantized periods. Remember that the gauge transformations for an ordinary U1 connection involved an angle-valued gauge parameter, a scalar that was 2 pi periodic. This is the one-form higher version of that. This is a one-form gauge parameter, and the analog of being 2 pi periodic is that this thing is actually a U1 connection with quantized fluxes. Okay? Now, if we have, right, so the claim to fame of background gauge fields is that whenever you give me a symmetry with some current, or even a discrete symmetry, but we'll stick to the case with currents, then I can enrich the Lagrangian of the theory by coupling it to those background fields. And the fact that the theory had the symmetry to begin with means that the theory in the presence of background fields enjoys a background gauge invariance. So what we have to figure out is how to take the Maxwell Lagrangian up on the first line up there and couple it to BE and BM in such a way that the resulting theory is invariant under these background gauge transformations. And I claim that the correct way to do that is to write the following action. The first part is kind of intuitive. There's a kind of minimal coupling of the electric two-form gauge field to F. So you replace F by F minus B electric everywhere. I'll explain why in a minute, but that's what you do. And then there's a separate term that involves a coupling, kind of BF-like coupling of B magnetic to F. So this is a BF term which involves no star, right? So first of all, why is this roughly speaking the correct thing to do? Well, this coupling is kind of obviously correct because you see that BM couples to the magnetic two-form current. If you look at the term that's linear in B electric here, if you expand this out, this quadratic term, and you look at the term that's linear in B electric, you see that B electric couples to 1 over E squared times star of F, which is precisely the electric coupling. So the linearized level, these background fields coupled to the corresponding currents. Now there's also a quadratic term here, which is a kind of Siegel type term, which is needed to ensure gauge invariance. So I claim that the correct transformation of A under these symmetries is as follows. Claim that you should take the electric U1 connection, and you should shift it by lambda 1 like this. Lambda 1, electric. It does not get acted on by lambda magnetic. First of all, note that this is a non-trivially consistent thing to do, because both of these are U1 gauge fields with integer fluxes. So if you add them with integer coefficients, then the sum will also be a U1 gauge field with integer fluxes. If you put some random number there, like pi, you would ruin the flux quantization. This is closed. The same words that I said about the one-form gauge field yesterday. You should really think of lambda as being an ordinary U1 connection, like A itself. And that's what I'm saying here. You can add them precisely because they're the same type of geometric object. Very good. Now, one thing you see from this actually is that the Wilson loop transforms under background gauge transformations precisely by the holonomy of the lambda background parameter around the Wilson loop.
This is one of the ways you can see that the Wilson loop is charged under the symmetry.
How is it charged? You just told us it's not charged.
Okay, I knew that. The moment I said that, I knew that I was going to get myself back into this discussion. So I'm going to have to clean it up. Now I'm going to have to clean it up. All right. So let's say this properly. So the Wilson loop is e to the I QE times this, right? And if I do this background gauge transformation, then it shifts by, so this is, let's call this W, and WQE shifts by e to the I guess there's a QE, the integral of lambda E around the loop times W. Now, this is the transformation under a background gauge transformation. Okay, this is a more general transformation than the actual global symmetry itself. How do you find the global symmetry inside the background gauge transformations? You look at those global symmetry. You look at those background gauge transformations that leave B 0. Right? If you're a person in flat space and you study the theory in the absence of background fields and you want to keep it that way, you set B to 0. This is what we did before, and then the only things that you are actually considering are flat lambdas. Okay? And so you see that the Wilson loop transforms by the holonomy of a flat lambda field. But a flat lambda field requires non-trivial topology. Right? You need a non-contractible loop in order to have a flat lambda. And this is a reflection of what I was saying before.
Okay. Flat non-trivial?
Sorry?
Flat non-trivial.
Yeah.
Yes.
Excuse me, like how the BF term is gauge invariant under the one-form electric transformation?
We haven't gotten there yet. I haven't argued to you yet why this thing is the right thing and and to what extent it is or is not gauge invariant. So I've just written it down. So let's discuss that. So you're jumping exactly to what I want to say next, right? So the claim was that we should attempt to write an action that is gauge invariant under B electric and B magnetic. Now the first term is clearly invariant under electric gauge transformation, so it's done. If you consider magnetic gauge transformations, that this becomes d lambda, and you can integrate by parts and get 0. There's one piece, though, that is suspect, right? You now have this B magnetic here, and this F now shifts by d lambda electric. And this transformation generates a term that is not quite invariant, but it's not invariant in a very mild way. Right? It's not invariant, but it spits out a C number. I'm going to have to get the stick. And what we're left with is essentially the variation of this term under electric gauge transformations. So the variation of S, when we shift A goes to A plus lambda electric, and the B's transform in the way that I said, oops, is that you get the original action plus the term that comes from doing the electric gauge transformation on F here. And that's I over 2 pi times B magnetic wedge D lambda electric. So this action is almost invariant, and it fails to be invariant by a term that only depends on the background fields and the gauge parameter. So this is a C number. And this is a totally allowed thing. This is a quintessential property of having a symmetry within a 't Hooft anomaly. Ordinarily, if you had a symmetry without an 't Hooft anomaly, this would have just been dead invariant. If it's invariant up to shifts by a C number, then that means that the symmetries we're discussing have an 't Hooft anomaly. Now, you might have thought that you can fix this problem by doodling around with the way that you couple F to background fields here. Maybe you would have said, oh, I made a mistake. I should have written F minus B electric instead of F. But that only modifies this action by a local counterterm of the form B magnetic wedge B electric. And that cannot cancel this. It can kind of move it around. It can change the nature of this. It can change the precise formula that comes out. But the fact that there's an irreducible piece that doesn't disappear doesn't change. So you can never annihilate this transformation by modifying this action by local counterterms. And I'll make that obvious in a second when I write a kind of anomaly inflow action for this. Notice also that this is a mixed anomaly between electric and magnetic. Right here I have the electric gauge parameter and the magnetic background field. Right? So this is not a self-anomaly in any one of the two symmetries, but it's a mixed anomaly. This is very much like the mixed anomaly between momentum and winding in the compact boson.
Yeah, I just did not get the point. Like if you shift the BF term like BF minus B electric, then it's clear that like transformation of F cancels the transformation of B electric.
Yeah, but now the gauge transformation of BM is no longer okay, because you see the reason why the gauge transformation of BM was okay is because F is closed, but B electric is not closed. So when you integrate by parts, you get something non-zero.
Yeah, but only in terms of background fields again.
Well, it'll again be a C number. It'll be a different C number, but the claim is you can never make it zero, no matter what counterterm you add. Very good. We will soon discuss what it means to gauge some or all of this one-form symmetry, and of course the presence of this anomaly means that we can't gauge too much of it, roughly speaking. There's an obstruction to gauging both one-form symmetries, and if we want to gauge a subgroup, we have to pick an anomaly-free subgroup. Now, the standard useful way of capturing the content, the kind of scheme-independent, counterterm-independent content of ordinary anomalies is to write an anomaly inflow action in one higher dimensions, right? So for example, for ordinary triangle anomalies for zero-form currents, we would write some kind of Chern-Simons term in 5 dimensions if we're doing 4-dimensional field theory, in 3 dimensions if we're doing 2-dimensional field theory. These anomaly inflow actions are very closely related to the kind of invertible phases that Max was talking about yesterday. In some contexts, they're exactly the same. And the notion of an anomaly inflow action also generalizes very nicely to two-form symmetries and to two-form background fields. Right, so how does this work? You're trying to find a 5-dimensional action that has the property that when you put it on a 5 manifold with a 4-dimensional boundary, so imagine that your field theory that you're studying 4-dimensional is here. Here's your M5. You're trying to find an action that is gauge invariant on closed 5 manifolds, but has the property that when you put it on 5 manifolds with a boundary, it's not quite gauge invariant and precisely spits out this anomaly. And the 5-dimensional action that does this is a BF type, I don't know how to call this exactly, BB type action, like this. You can write B electric, wedge DB magnetic, that's a 5 form. And it's also gauge invariant if M5 is closed. You can check that. That's because this coefficient is kind of properly quantized in units of 2 pi. But when you cut the 5 manifold open and put a boundary M4 here, then you see that the gauge variation of B electric, right, will spit out D lambda electric, and that will lead to a boundary term which is precisely lambda electric times dB, which looks like that, up to integration by parts. And the fact that you have this 5-dimensional anomaly inflow action, which is not a boundary term, it's a genuinely 5-dimensional term, means that the anomaly cannot be cancelled by any 4-dimensional local counter term in the usual way. Very good. Yeah.
So if we consider the diagonal part of the magnetic and the electrical waveform symmetry, where there will be a QU waveform anomaly?
Well, you tell me. This is the anomaly. What do you need to do?
So we consider the diagonal part.
So what does that mean for the background field?
Okay, yeah, then they are.
Yeah, so if you want the diagonal part, you set them equal to each other, right? And then this term vanishes by. So the diagonal symmetry is non-anomalous. Yeah.
So you also introduced the mass term for BE. What is the physics behind it?
There's no mass term because BE is non-dynamical.
Well, it could be.
It could be, but it's not.
I mean, they are continuous, so I imagine that you can put kinetic for both. But
you can. But again, they're not dynamical. So a kinetic term would be some kind of counter term that doesn't do anything particularly interesting. Yeah. Indeed, if you want to gauge BE or BM, all of it, then you need to make them dynamical and you need to add kind of standard kinetic terms and so forth. Yeah.
And here there is also a symmetry because only BE require a mass term, not BM, in this frame.
Right. Well, you can make this a little more symmetric by choosing counter terms. I've chosen here a kind of asymmetric presentation. By using the counter term, you can make it look a little bit more symmetric. Yeah. Yeah, that's something you can do, totally legitimate. I will not discuss gauging the whole continuous symmetry, but I'll discuss a little bit the discrete gauging. Yeah.
So for counter terms, so am I allowed to add stuff to make it sort of not gauge invariance? Like, can I get rid of this BE squared with the counter term?
Well, it's the other way around. The BE squared is there precisely in order to cancel something that otherwise would be there. If you cancel this BE squared is there in order to make sure this expression is fully invariant under electric gauge transformations. If you eliminate this BE squared, you'll get a leftover C number piece that will be like very annoying, kind of like D lambda E wedge star D lambda E or something like that.
Yeah. I guess I'm wondering because generally, if I want to couple something to gauge field, I just write like J mu A mu or something.
No, but you know that that's imprecise. You know that even for ordinary symmetries, there are Siegel terms. For example, if you take scalar QED, if you just write A mu J mu, you'll miss the kind of quadratic A squared phi squared coupling that's present in scalar QED. So A mu J mu is a kind of suggestion for what the right thing is. It's the right thing at linear order, but in order to have gauge invariance at higher orders, you might need to add quadratic corrections as well. Yeah. Okay, I'm gonna have to make some sacrifices very soon.
No.
Not you. Well, let me think. It's okay. Whatever I don't cover, it'll be an exercise. A la Bruno. It'll be many exercises.
I would suggest to take less questions.
Oh.
I think it's important to cover. This is recorded. This is a contribution for the future.
That's a lot of pressure.
And I should have censored myself more.
Okay, no, it's fine. I think there's a path forward here. Okay, so I think what I'll do is I'll wrap up the discussion of free Maxwell theory here, and then I'll finally start adding some matter, and then we'll see how far we get. All right, let me move this up. All right, at some point, there's only so much fun you can have with free theories, although you can have a lot of fun. So let's finally discuss an interacting model. In fact, it's the model that we're just discussing with the non-minimal coupling, the quadratic coupling between the scalars and the gauge fields. So we'll discuss, what in some circles is called scalar QED, and in other circles it's called the abelian-Higgs model. I don't know. I don't know what the overlap is. In textbooks, people call it scalar QED. All right, so we'll take Maxwell theory, and now I'm going to write it in the pedestrian way. And I'm going to add to it one charged scalar field, which I'll call H for Higgs field, and it'll have electric charge QE. I'm not adding any magnetic charge. So I'm going to add kinetic terms for H, and then a gauge invariant potential. And here is where the Siegel terms come in, right? The covariant derivative involves this. And if you expand this out to linear order in A, you get the coupling to the current, but there's an A squared H squared term. All right. And this is in principle any U1 invariant potential. We'll later take it to be something simple, but it could be anything. I'm not worried about things like renormalizability or something. All right. The coupling to background fields is exactly as before, right? The coupling to BE and BM is exactly as before. Although, as we'll see in just 1 second, not all of the one-form symmetry survives once we introduce this H field. Okay? Well, so which part survives? It's easy to see that the magnetic part is completely intact, because I've not added any magnetic charges. This is a standard U1 gauge theory, and therefore my gauge field is still a standard U1 connection, and F is still dA, and therefore you still have the Bianchi identity, right? That says that dF is 0, and so U1 magnetic is completely untouched. However, the electric one-form symmetry is explicitly broken. Not spontaneously, explicitly. So it's just destroyed by the presence of this charge H field. And there are various ways of seeing that. Maybe a simple one is to remember that the corresponding equation in free Maxwell theory was just the Maxwell equation, d star F equals 0. If you look at Maxwell's equation in this theory, it says that d star F is not zero, it's the electric current, which is some bilinear in H with some particular coefficient. This is probably a 3 form, I guess. And that's non-zero. So at the very least, you don't have a continuous one-form symmetry. The current is not conserved. This J electric is not a total derivative, so you can't fix it by somehow redefining the current. And then the question is, could it possibly be that U1M is broken not to nothing, but maybe a discrete subgroup? And the claim, so U1 electric. And the claim is that U1 electric is broken to its ZQ electric subgroup. How do we see that? Well, where was this equation important? This equation was the equation that guaranteed that if you take a Gaussian flux integral, an electric flux integral, and you deform the Gaussian surface by a little bit, then the answer doesn't change. Right? That required d star f to be 0, and then you could use Stokes' theorem to prove that. If you do exactly the same argument, you'll now find that the difference between the Gaussian flux integrals will be the integral of the right-hand side over the kind of interpolating 3-manifold. So you'll get the integral of J electric over this cobordism, and that's non-zero. But there's a kind of glimmer of hope here, right? Because the charged field carries charge Q electric, and therefore it's sort of intuitive, though not particularly simple to make explicit in this context, that the integral of J electric should in some sense be a multiple of QE, right? If everything charged in the universe is a multiple of QE, then it stands to reason that this integral over J electric is also a multiple of QE. And if that's true, then you can still show that these kind of operators, the exponent, can everybody see that right there? Yeah. The exponentiated electric charge operators are still topological as long as I don't put an arbitrary angle here. Remember in the previous case I was able to put an arbitrary angle here, and now I can put an arbitrary integer multiple of 2 pi over QE, right? Because if I do the deformation argument and I pick up a multiple of QE, this QE will cancel, and therefore I'll get 2 pi and times an integer times I, and that thing will still be topological. So this is still topological. And this is the topological two-surface that generates this discrete ZQE symmetry. Very good. Now, once you know this, you can go ahead and you can try to mimic many, many aspects of our previous discussion in the context of this broken subgroup. I won't have time to necessarily kind of cover this in all technical detail because it's a little bit technical. But for example, you need to reduce the BE background field to be no longer a U1 connection, but instead to be a kind of ZQ background field. So BE will be flat, and it will have holonomies that are valued in ZQE. And there's a kind of nice way of rewriting the holonomies of B in terms of the cohomology with coefficients in ZQE. So that's a nice thing to do. But, well, because it's a little bit technical, I think I'll try to get to the physics of that we can kind of learn in this model and what it tells us about, breaking and non-breaking of the remaining one-form symmetries and by looking at the phases of this model and by looking how the one-form symmetries are realized in these phases, we'll get a much richer idea of the sort of interplay of higher symmetries and gauge theory phases than we did in the Maxwell theory. Maybe before I do that, let me review what is probably the quickest, but also the most intuitive and useful argument for why this U1 electric is broken to ZQ. And this is an okay argument, but one that's really nice and almost always useful involves thinking about which line defects can end and which cannot end. Remember, I was emphasizing yesterday that one-form symmetry is a kind of flux conservation symmetry which prevents lines from ending. Right? So, for example, if we have a 't Hooft line of any magnetic flux, right, it can't end. It has to either go on for infinity or it has to loop back on itself, and that's still true in this model because U1 magnetic is conserved. But if you take this to be a Wilson line of general, well, let me not call it QE because now QE is the charge of the Higgs field. Let me call this N. Right? Then there's a question of when this thing can end. Well, we've already discussed that an open Wilson line, right, if it ends in the middle of your space-time, it's not gauge invariant. Instead, it transforms under gauge transformation with a phase that looks like kind of e to the either plus or minus in alpha. If you do a gauge transformation with angle alpha of x. And so that means you have to stick a charged local thing here that carries precisely charge n. Now, in this model, my elementary local field is h, and it carries charge QE. And you, of course, can make composites of h. You can take h squared, h cubed, whatever, but you can only make local charged things that carry integer multiple of QE. So that means that if n is divisible by QE, then this line can be screened, this line can end, and therefore kind of at the very least, the one-form symmetry has to be broken down to ZQE. But any line that, for example, any line that does not have in its charge a factor of QE cannot be screened. So for example, if you just take n to be 1, if you just take the fundamental Wilson line, then this cannot be screened. I'm assuming here that QE is not 1. If QE is 1, every line can be screened, and then the one-form symmetry, the electric one-form symmetry, is just gone. This is extremely useful because it also gives the correct answer in non-abelian gauge theories and much more complicated examples without necessarily introducing a lot of machinery. All right. So let's discuss the phases of this model and see how the one-form symmetries are realized.
So can I just clarify it for myself? So what you said is that Wilson line, for example, is n equals k times QE can end at h in the power of t.
For instance, or any other such operator that carries charge. Okay, yes. Mm-hmm. So let me imagine dialing the potential so that we have sort of two phases. If you consider V to be the sort of standard quartic potential that we discuss in Higgs models, and you can dial the mass of the Higgs field, and if it's positive, then the Higgs field doesn't get a VEV, it gets a very large mass, you can integrate it out, and if the Higgs field gets a VEV, then you're in the Higgs phase. So I would like to discuss these two phases. All right, so let's take MH to be large and positive. Then H gets no VEV, and H is very heavy, so we integrate it out. And at low energies, you're just, in the deep IR, you just flow to free Maxwell. So this is a theory we've by now beaten to death. But if you remember that you have a heavy H field and you integrate it out, not just, you don't just throw it away, but you actually integrate it out and you compute the induced corrections to the low energy effective action, you will get Maxwell theory plus higher derivative corrections, right? So, you'll get things like f to the 4 divided by m to the 4. There are two such terms, and then there are higher terms like this. So you'll get something which, loosely speaking, is called the Euler-Heisenberg effective Lagrangian. When you integrate out a massive charged particle, you get Maxwell plus higher derivative corrections. So at very long distances, right, in the usual effective field theory way, you can throw out the higher derivative corrections. The theory is dominated by free Maxwell theory. So the IR behavior of this model is exactly like we discussed in free Maxwell theory. The one-form symmetries are spontaneously broken. The photon is the Goldstone boson of the one-form symmetries. Now, the one-form symmetries here are not quite the same as the one-form symmetries of Maxwell theory, right? Microscopically, this model has a U1 magnetic. That's spontaneously broken, and the photon is the Goldstone boson for that. The ZQ is also spontaneously broken. But in fact, at long distances, if you look at this low energy effective action, the ZQ is enhanced back to a U1 electric, right? This model doesn't have any charged particles. The charged particle had mass m. We integrate it out and we forget about it. And you can check for yourself that if you write down Maxwell's equation in the presence of these higher derivative couplings for F, they again give you a conserved electric two-form current. Roughly speaking, the conserved electric two-form current will look like before. There'll be a star F, and then there'll be kind of cubic terms suppressed by m and so forth. But because everything is a function of F only, you still get a nice gauge invariant two-form current, which is not exactly the same as the original Maxwell one, but gets small corrections, right? So here we have a situation where even though microscopically we broke the one-form symmetry, the electric one-form symmetry explicitly, it kind of re-emerges in the d pi r in this Coulomb phase, right?
And further, it is spontaneously broken?
Yes. It emerges and it's spontaneously broken. That's right.
It's a bit weird how it emerges.
Yeah.
It doesn't seem to be an RG effect.
I don't know what that means.
Well, usually if you have an emergent symmetry for normal symmetries, there could be some irrelevant operators which flow to zero.
Right. So let me comment on that. Irrelevant operator. Yeah, let me comment on that. Yeah, so that's a good point. I wanted to say that. So indeed, for ordinary zero-form symmetries, you would expect that if you go to high enough order in the derivative expansion, you will eventually encounter an irrelevant operator that explicitly breaks the symmetry. For example, baryon number is broken by dimension 6 operators in the standard model. Not by normalizable ones, but by dimension 6 ones. As I told you yesterday, because one-form charges live on two surfaces, they don't act on any local operators. So there is no local operator in this long-distance effective theory that carries anything like a one-form charge. And therefore, there's no sense in which you can add a term to the Lagrangian that captures the breaking of the symmetry. But that's a little bit weird, I agree. That's unusual. But it's a feature, it's not a bug. But it actually tells you something. What it tells you is the following. Normally, if you have a higher derivative operator in the low energy effective action that breaks the symmetry, it means that the breaking is a kind of power law effect in the low energy theory. What this tells you is that the breaking is actually exponentially small. And exponentially small effects are not captured by the low energy effective theory.
So it's a pair production that is.
Yeah. So the amplitude, for some, if you want to have some process that actually picks up on the one-form breaking and measures some observable at distance r, it's kind of exponentially suppressed in the mass of the particle, the H particle that breaks the symmetry. Okay. All right, so let's move on to the Higgs phase. At least let's get that started. If we don't finish it, then I'll have another lecture later in the afternoon to finish. Let me do that. Let me do that here. So in the Higgs phase, right, we have a charge QE Higgs field. So let's imagine that M Higgs is large and negative. I'm just taking it to be large so I can do classical physics. I don't have to worry about quantum corrections. I take it to be large and negative, then H does get a VEV. And because H has electric charge QE, it Higgses the U1 gauge group down to ZQE. It doesn't Higgs it down completely, it Higgses it down to ZQE. So this is the U1 gauge symmetry. In some sloppy sense, we say that the gauge symmetry is broken to ZQE, and because this is not quite correct, we instead use the word Higgsing to sweep under the rug all the imprecision of the other statement. And the model is gapped, right? The photon gets eaten by the angular mode of the Higgs field and gets a mass. The Higgs field gets a mass. The radial component of the Higgs field gets a mass from the potential. So this is a completely gapped phase. But unless QE is 1, it has non-trivial topological order at long distances. It has a ZQE gauge theory. Which is the kind of unhiggsed part of the gauge group. The case QE equals 2 is kind of the famous example of a BCS superconductor, right, where you're left with Z2 topological order at long distances. Very good. Now I promised Elia I would stop at 10:40, so since it's 10:40, maybe I'll stop here and take some more questions, and then we can continue our discussion of the Higgs phase in the afternoon.
Yeah. Is there still a mixed anomaly between the ZQ electric and the U1 magnetic?
Absolutely.
So what happens? Where's my anomaly inflow actually?
Here. Maybe top. In the middle. That's too far from me.
I'm going to use all my time getting the board done. Right. So if you take this anomaly inflow action, this is the part I skipped over before when I said you could reduce the electric gauge field to be a ZQ gauge field, right? So this is the anomaly in the U1 times U1 case. If you break this to ZQ, then what you do is the following. You write, so B electric has to be flat. Once you break to ZQ, you can't have B electric fluxes anymore. So BE will be flat, and its holonomies will be integer multiples of 2 pi over QE. And there's a kind of this is the kind of conversion factor that you need to put from this kind of 2 pi periodic object to integer cohomology. And so you can define a field which you can call little b2 electric, and this little b2 electric is actually an element of ZQ cohomology. So b2 electric lives in H2 with coefficients in ZQ. And when you plug this into here, what you get is, what do you get? You get the 2 pi cancels. You get I, what do I want to say? Wait. Yeah, I'm even starting to question whether you need the 2. No, you do need the 2 pi. Yeah, I think that's right. You need the 2 pi, sorry, the 2 pi goes in 2 places. Yeah, let me leave, so there's a 2 pi over QE which goes here, coming from here, and then I'm going to move the previous 2 pi here. And what you get is the following. This B magnetic is still U1, right? So it has a flux, a 3-form flux that when you divide it by 2 pi is integrally quantized. So this is a class in H3 with integer coefficients. And now this class you can reduce mod Q, E. So you see this is a class with coefficients in QE, but you can reduce this mod QE and then replace this wedge by a cup. So this is mod QE. And so then this is now the reduction of the anomaly to the case where the electric symmetry is only ZQE, and it's still non-trivial. So we have a kind of ZQE valued anomaly rather than an integer valued one, but we still need to match it. And indeed, it's interesting to ask how it's matched. Of course, in the Coulomb phase, symmetries are all spontaneously broken, so it's just matched by the photon. The question is, how is it matched in the Higgs phase? Well, it's good that there's something non-trivial in the Higgs phase, right? If the Higgs phase were completely trivial, gap, boring, and trivial, it could not match this anomaly. And instead, this anomaly is matched by the leftover ZQE TQFT.
Yeah.
If I'm not mistaken, one can use this Toft anomaly matching argument if the symmetry is not spontaneously broken. And in this case, one should be spontaneously broken, the other not.
Toft anomaly matching, always. There's never a situation in which the anomaly is not matched. Spontaneous breaking is a way of matching the symmetry.
But like the original 't Hooft argument was like by gauging, introducing some theories that...
The original 't Hooft argument was to show that chiral symmetry in QCD is spontaneously broken. So clearly spontaneous breaking does match the anomaly. It's the other way around. No matter what, I don't know a counterexample to the following statement. Given any 't Hooft anomaly, spontaneously breaking the symmetries always allow you to match it. If you break the symmetry, if you spontaneously break the symmetry down enough, you can always match all anomalies in the universe. The hard part is matching anomalies without breaking symmetries. Then you need some kind of interesting degrees of freedom.
Okay, maybe in the homework, because we have only 15
Yeah.
minutes break.
We can continue.